x1 plus x2.
No. Here, not. Okay, this is position and momentum entanglement. Actually, this is very different.
Okay.
So here we need to put this way.
Smaller than 1.
Yes.
Okay.
I think it should be smaller than 4.
4.
这什么东西？
Okay. So it means the quadruple. Okay.
你刚才那个问题
The multiplication of the quadrature, it should be smaller than
，small than 4。Yeah。没有，这看你的定义啊。
Okay. 这是都是我 screen
测试。
Yes, it's true. So this is called the quadrature entanglement. It's entangled into quadratures. It's called the continuous variable entanglement.
Okay.
But if you want to look at this one, what you need to do is, so what you can do is that we have the SPDC, right? The signal and diagonal. So what we can do is that we can use kind of scanning. We can scan the position, okay, and try to look at the consequences. Okay, so basically what we can do is
测试喂
the delta X, you can it's like you can indirectly can calculate impedance and methods to calculate the delta P. So from here you can verify the position momentum entanglement in this case.
Okay.
This also yeah, similar. But here we are not looking the position momentum. We are looking
Well, but to me, it really looks like
没有。
Yes.
我看的是 face 的 screen。
Okay, I understand.
But I not feel like I want to verify this inequality very upon this condition. It is.
Okay.
Then that's
Okay. But no, this is the original one.
多测试喂
question not quadrature.
I see. Okay, thank you.
对。
测试喂
光的法
喂测试。
对。
但是我因为离体出力也是蛮小的，就只有100赫兹。
对，0.0几伽马。
对，但如果说我不调的话，我就是看到就是某个比例的法学学。
对。
那如果我调对了，瞬间调对了，那法学学就会瞬间减10倍。
他的学校，他对那个突风的定义是这个。
是啊，我固定的然后去使。
哦，你是固定哦，你是固定要用的。
对，
哦。
还可以，但是我去使。
对，他会突然变。
就是看我的讯号那个讯号量出来，它可能就会去法学学嘛。
对啊，对。
法学学当你在调某个比例降，我当然期待它确实你喜欢一点点降，对，降。但是这个法学学就是不太对。
因为录影机的关系，
这个录影有没有需要？
对，它会叫很快，会。
然后是超过这个底线的时候，这个法学学就出来。
对，因为这就是刚才有讲说，它有个 completion 机制，就是你的属性跟破坏型的这两个机制抗衡，所以它只有在达到那个最佳值。但是如果说你现在一面调，高比可以。
我不调，这样就是高比可以。然后我再去。
没有，它有个最配合的时候。
预测的时候，但是我少这样讲，
我了解。对，没错。所以你如果是固定高比，就是 input 高比，这样讲。
手动调。
对。
那个法学学突然变小，然后突然变大。
对，它就会从 coin state 然后一直降到 speed state。它会先降低啊，会降下去，然后再上。对，所以说你看到应该就是突然 variance 很大。
当我的高比会极大的时候，这个突然间有screening效率的放值很大。
对，因为跟越学越大，对。所以说但是你所谓调那个突风底径跟那个 omega 是不一样的。对，这个 omega 好像是它，我不知道实际上怎么样。你讲的是环轴嘛？没有不一样，那个。那个 omega 他们是用那种。 讯号，跟那个系统管理。就你
with his name on your tongue.
Yes.
你说那个 acceleration， 你讲是那个吗？
You have to remain this.
这个 对啊，对啊。但是问题是我们那时候是在 steady state， 我们那时候没有考虑就只是考虑场外在 steady state， 但是后来才把状态分别进去。我可以再考虑。
Excuse me, could you please translate? Okay. 不好意思。
可以录。
There are some more chairs over there. There are chairs there, and some more chairs there. That's fine, let's see. That's fine. So good afternoon, ladies and gentlemen. It's our great pleasure today to have Professor Gonzalez to give us a talk about LIGO. Professor Gonzalez was LIGO's spokesperson, and she has just been elected to be member of National Academy of Sciences of the United States, right? Okay, yeah, congratulations. And yeah, and LIGO now. Oh, please try to find a seat. Come in, please. LIGO now is quite well known to people even not in this field because of their detection of gravitational waves. And today, Professor Gonzalez will tell us the whole
story, the hardworking of Ligo project for 20 or 30 or even 40 years, right? Okay. And before listening to the talk, because this is also part of the NCTS, the 20th anniversary activities, so I would like to invite Director Zhu Changxin to say a few words.
As NCTS Director, first I would like to welcome all of you for this activity. As Han Guang mentioned already, it's the 20th year anniversary for NCTS. Over the 20 years, there's been a lot of development in science. And I'm very happy that NCTS can be part of this witness for the discovery of gravitational wave and also black hole through the Ligo experiment. It's an exciting time, I think. I'm happy all of us are here. Yeah. So I won't take you more time.
A warm applause to welcome Professor Gonzalez.
Thank you so much for the invitation. I'm very glad to be here. This is my first time in Taiwan. I certainly hope not the last one. And I've been enjoying my visit very much. So I want to tell you about the story of the search, and now I can say the finding of gravitational waves. Many of you have probably seen this waveform, but I want to tell you how we got there, and then how this is only the beginning of a very long journey, not the end. Yes. Okay, that's enough. Just need the one. So let me first give you a brief introduction about gravitational waves. They are, sometimes I like to say, a straightforward, one of the few straightforward consequences of Einstein's equations. And you might have seen Einstein's equations, and you might have heard they are very complicated. They don't look complicated, they look like these. They say that the Einstein Tensor, which is a four-dimensional tensor, and it's built from the space-time metric. So we have a four-dimensional space-time metric that tells us about the distances and times between all points in space-time. So this Einstein tensor is constructed from derivatives of this metric and multiplied. So this is going to become a nonlinear differential equation. And on the right-hand side, we have the stress-energy tensor. So this is telling us where the matter is in the space-time and how it is moving, where the mass and the energy, because mass and energy are the same thing. So that's why this is the stress-energy tensor. So one of the things one can do is try to find a vacuum solution, like for the electromagnetic waves, for Maxwell's equations. And if you set this equal to 0, and you make some approximations, like the space-time metric is just the flat space metric that we use for everything else in physics, plus a very small perturbation, then and only then you get in here a wave equation. A wave equation for perturbations of the space-time metric that travel at the speed of light. Those are the gravitational waves as predicted by Einstein's equations. Now, how to measure them is you have to remember how to interpret the space-time metric. This is a dimensionless metric. It has relationships between times and distances. And what the perturbation that we are talking about here can be measured as a fractional change in distance. So what that means is that if you know the amplitude of the gravitational wave, distances are going to change in a wave pattern, but with the same fraction. So the longer the baseline you measure, the larger the change. The fractional change is what defines the amplitude of the gravitational wave. Another aspect that can be derived from here is that it is a quadrupolar, it is a transverse and quadrupolar wave. So if the wave is traveling in this direction, then the perturbations, perturbations are in the transverse directions, and one way of describing them is that if you have free particles at the same distance from a center, defining a ring, a circular ring, and there's a gravitational wave, then the distances between those particles are going to change such that even though in principle nothing is moving, there are no forces, the distances change such that what looked like a circle now looks like an ellipse, and then half a cycle later it's circle again, and then 3/4 of a cycle an ellipse in the other direction. This is one of the polarizations. We call this the plus polarization, and this is the cross polarization, you might guess, because the ellipses form a cross. So those are the two polarizations of gravitational waves. So this is what we want to measure, these changes in distance, how this distance becomes that distance and back again. Now what produces these waves? Actually, Einstein made these predictions very soon after. He published a general theory of relativity in 1915. In 1916, he came up with a paper with this wave equation. In 1918, he was already publishing the formula I'm going to show you now that we call the Quadruple Formula that tells us how the gravitational waves are produced. However, not only he had several mistakes in those papers, that took some time to discover, but also even he putting all these, even he and then most people afterwards putting all these numbers together thought that these things were going to be impossible to measure. So let me show you why he thought that. This quadruple formula tells us how those perturbations are produced by matter. So now you want to put matter in here and see how the matter produces those gravitational waves. And you're looking at the effect of the motion of the masses on the space-time far away in the radiation zone. And the approximate formula you come up with, or he came up with, actually it's not so simple. This one, the wave equation is kind of simple to get. This equation not so much. Is that the amplitude of the gravitational wave is going to be proportional to time derivatives of the mass quadrupole. Mass quadrupole, you might remember, is defined from distances of masses of the particles in the mass, of the elements of mass. So a spherical mass does not have a mass quadrupole and then does not produce gravitational waves. If you have an ellipsoid and it is rotating, for example, that would produce gravitational waves. If you have two masses, like in a binary star system, that has a quadrupole, and again it would be rotating, it would be producing gravitational waves. But the spherical mass does not produce gravitational waves. So if you have large mass quadrupoles, large masses, astrophysical masses, and they are moving very fast, speed of light or near speed of light, then you might make these things very large, but they are multiplied by Newton's constant, because Einstein's theory is the theory of gravity, divided by the speed of light to the 4th power, divided by the distance to the source. Notice that this is distance and not distance squared, because this is the field and not the energy of the power. So this number is very, very small. Even if you put large masses and very high speeds in here, you get almost nothing. Nothing to measure, he thought. Well, other people thought different. But let's put the numbers to see how small these things get. So let's think about a binary star system. Like this is coupling somewhere. Let's think about a binary pulsar system where we have two neutron stars that are rotating around each other. We can tell how fast they are rotating if one of the stars is a pulsar, and we get the radio signals from that pulsar. So we have some astrophysical evidence of this. So we know how to calculate the mass quadrupole. We know how to calculate the derivatives because it's mostly circular motion. So we can calculate the energy that's going away in these gravitational waves that's making the stars getting closer and closer. So the prediction is that we are going to see a sine wave of increasing amplitude and increasing frequency, because the stars are closer faster, so the frequency is larger because it's faster, but the amplitude is also larger because of that, until they merge. Two neutron stars would merge and form a black hole. That's how black holes, that's one of the ways black holes are formed. So this is a predicted waveform, and this would travel more or less in all directions. With different amplitudes, but more or less in all directions. The strongest direction would be perpendicular to the orbit. So, how far does it get? How large does it get? Would it get largest just before coalescence? How often does it happen? That also matters if you want to measure this. Well, these kind of systems, we as astronomers actually estimate that merge in our galaxy about once in 10,000 years. So calculating this amplitude for a merger in our galaxy is not good because you would have to wait a long time. So if you want to calculate this amplitude for things that happen farther away. So let's think about the Virgo cluster, where the Milky Way is. That's 16 megaparsecs away. How that has a frequency. These coalescences are supposed to happen once every 50 years or so. How strong would be that before coalescence? Well, the calculation says 10 to the minus 21. So this fraction is 10 to the minus 21. Now, you may not carry numbers in your head, but if you use a baseline for the distance between the Earth and the Sun, that's an atomic diameter. A bit larger than a hydrogen atomic diameter, but still an atomic diameter. So that's really small. Who can measure that on Earth, where you certainly will have smaller baselines? And how do you measure it? Well, in the 70s, we began proposing to measure this with interferometers. Interferometers seem a nice way to make very precise measurements. They have been used in precision measurements in many experiments. And as you might remember, an interferometer measures the difference between two distances. They measure the interference pattern that comes out of the detector on a photo set. And that's exactly what you want to do here. You want to measure the difference between perpendicular distances that make this ellipse different than the circle. So that's what an interferometer does. 10 to the minus 21, however, is very small. How big do you need to make your interferometer? You certainly cannot make the laser go to the sun and come back. But it turns out that you can make interferometers very precise. And I'll show you how precise. Before that, since I'm talking here not just to physicists but astronomers, I will also remind you that gravitational waves are old news. We detected them on going through Earth very recently, but we knew they existed for a long time. And that's because we know about neutron stars. Let me see if I can get this going. So we know about neutron stars. We know they get close. We know they emit gravitational waves. Measuring the gravitational waves is difficult, but measuring how close the stars get is not so difficult now. In the 70s, people discovered, Hudson Taylor discovered the first binary pulsar system. And it turned out that it was a system when the stars were close enough that Taylor thought, we could measure here the stars getting closer. And they did. Measuring it over the years, this is a plot of the quantity that is proportional to the size of the orbit. So this is showing that the orbit is getting smaller versus the year of the observation. And notice that this starts in the 70s and ends in 2005, although we do have 10 more years of data. And the orbit is getting closer, it's getting smaller and smaller. And you might remember that they got the Nobel Prize in 1993, long after the discovery and the measurements, because of this. So gravitational waves were known to exist. Now the measurement of gravitational waves going through Earth is what we want to do. Again, in the 70s, people in the US proposed, people from Caltech and MIT, proposed to build 2 detectors, 2 Michelson interferometers, although I'll tell you later that they're not just Michelson interferometers, 4 kilometers long, and build 2 in the US, because you're making measurements of signals that are so small that you want to see them in 2 places at almost the same time if you're going to say that they're coming from space and not from natural environmental disturbances near one detector of the other. So you needed to convince a lot of people to invest a lot of money in an experiment that many people thought it was impossible. And they did that. I don't know how they did it, but they did that. In the 90s, these 2 observatories were built in the US, the Ligo Livingston Observatory in Louisiana, very close to where I live in Baton Rouge, and the Ligo Hanford Observatory in Hanford, Washington. They were built in the 90s with a technology that was going to deliver this 10 to the minus 21 sensitivity, or at least it was promised to deliver that sensitivity, but I told you that that only promised, had only an expectation of a detection of these binary neutral star systems once every 50 years. So that wasn't going to be enough. That was not quite the motivation to build this. The reason, the motivation for the agency, the National Science Foundation, was that in the time it took to build and test this technology, working everything well at 4 kilometers baseline, the technology was going to improve 10 years, in about 10 years, and then there was going to be better technology, about 10 times better, to install in the same facilities to make the detector 10 times more sensitive, and that would have guaranteed detections. So that was the idea. And it was not just people in Caltech and MIT. In 1997, that is 20 years ago now, the Ligo scientific collaboration was formed. That was an international collaboration, not just with people in the US, in many institutions, not just Caltech and MIT, but also people in Europe and people in Australia, and then it grew to people in many other countries, including Taiwan. So the Ligo scientific collaboration now, 20 years after being formed, has about 1,000 scientists from more than 90 institutions in 15 different countries in most continents. We're still missing Africa, Antarctica. You heard that I was a spokesperson during this very exciting time of the discovery. My term ended in March, and the current spokesperson is David Shoemaker from MIT, and there's a deputy spokesperson, Laura Cagonati from Georgia Tech. So this is a very strong teamwork. We really do it all together. And sometimes I feel a bit embarrassed when people recognize me, and I always accept the recognition on behalf of all these other people that have done the work with me. So, let me show you the performance of those initial LIGO detectors and the expectation for what we call the advanced LIGO detectors. We operated the initial LIGO detectors between 2005 and 2010. In about 2010, we got the best sensitivity that we have, and the way we describe the sensitivity is a bit strange, except for those experimentalists that like to use spectrum analyzers. How many people have used spectrum analyzers? Now? 90? Okay. Okay, I feel a bit better.
Now it is low frequency range. Typically we operate LIGO megahertz and gigahertz.
Okay, well, the principle is the same still. So what this curve is describing in terms of amplitude per root hertz versus frequency is the noise of the detector. At the output of this Michelson interferometer that we have, what we have is the signal from a photocell that is not zero waiting for a gravitational wave that will make it go. It's always some kind of noisy signal produced by disturbances in the detector. So that noise is what we need to quantify to see how sensitive our detector is. The lower the noise, the better. So we make an amplitude spectral density of the noise, essentially calculating how much power, if you square this, how much power density there is in each frequency bin. And what you get is this curve, again at our best, for strain noise. Remember, this is fractional distance change versus frequency. So this is telling you that about between 100 and 200 hertz, that's our sweet spot. That's our best sensitivity. And then we have not so good or less good at these frequencies and quite a bit less good at these frequencies. But there are about 3 regions in the noise spectrum. Now notice the numbers here. This is 10 to the minus 21, 22, 23. I told you that we wanted 10 to the minus 21, so you would say, well, this got 10, 100 times better. That's not quite true, because what you want to do when you want to see how much noise this really means is, for example, integrating the noise in a frequency band that you're interested. So if you integrate the square of this noise between 100 and 200 hertz, you have to square this, integrate versus frequency, that gets rid of these hertz in there, and then take the square root. That is similar to the root mean square of the time series filtered between those frequencies. And if you integrate this between 100 and 200 hertz, you get 10 to the minus 21. A bit less, but about that. So we got the sensitivity that we had promised. But you might remember that in 2010 or 11, we didn't make any announcement. We didn't discover anything. We took data for several years, searching for several signals, many signals, we didn't get any. How far does this let you see? Well, for these signals from binary neutron star coalescences, does everybody hear that feedback? Just me? For those binary neutron star coalescences, you can tell that if you have this noise and the signal is at some distance, you can calculate what is the signal to noise ratio you are going to measure in your detector. So if you want a signal to noise ratio of 8, which is a reasonable one, although you would say that that's a low threshold, but a signal to noise ratio of about 8, how far does that let you see? And the answer is for this curve 15 to 20 megaparsecs. That is about the distance to the Ligo cluster. That is what we had said in the beginning. So we didn't see anything. No astronomer was surprised at this. But in the meantime, like promised, there was better technology that had been developed to have this concept of advanced LIGO technology that could promise a curve that would be 10 times better at most frequencies, much better at lower frequencies, and would let you see these systems 200 megaparsecs away. And this is the average distance. If the system is optimally oriented, you can see it more than twice as far. But this is the average reach. So that is when you would expect to see many coalescences per year, but you still have to get there. So how do we get there? Well, first, what limited us in here? At these high frequencies, the answer is relatively easy, and this is relatively easy to get. This is the quantum noise in the laser. The laser is made out of photons. We are counting photons in a photocell, so we are victims of counting statistics, what's on statistic for those photons in there. So we do have that counting uncertainty. Short noise. If you do electronics, if you're an electrician in E, you know what short noise is. This is short noise. It has this form because we do have optical resonant cavities that give it a frequency dependent. But this is a quantum noise in the laser, essentially. This is the seismic noise. The seismic noise filtered through very severe, very aggressive seismic isolation systems. We had the mirrors hanging in pendulums. We had those pendulums hanging from masses and springs, like shock absorbers. But even then, with all that filtering from the ground noise, you got this much motion, and it rises very, very fast with frequency. And here in the middle, there's a lot of contributions in there, but even if we had gotten rid of those, we would be limited fundamentally by Brownian motion. Because in a microsome, you are measuring these distances between mirrors. These mirrors are at room temperature. They are vibrating because the atoms are at room temperature. So you have kT of noise, Boltzmann constant. So you can calculate how much that noise distributed in different frequencies. That's not very easy, but you can do that with certain assumptions, and you get this limited here. So we knew what to do to get better than that, and that's what was done for advanced LIGO. We got better seismic isolation to improve the low frequency noise. Instead of single pendulums, we had quadruple pendulums. Instead of masses and springs, we had masses and springs, but measuring the distance between the masses and then canceling it, so it's an active seismic isolation system. At these frequencies, we have reduced Brownian noise. And you would say, well, reduced Brownian noise, that means reduced temperature. It turns out that you can do other things than reducing temperature to reduce the Brownian noise if you're interested in certain frequencies. When you calculate what is the noise at different frequencies, what you have to ask is how much of that kT energy excuse me, how much of that kT energy is in different frequency beams. Turns out that there is a theorem in statistical physics called fluctuation dissipation theorem. How many people have heard of that before? Quite a few more than spectrum analyzers. That's good. That tells you that if you don't have any dissipation in the system, then all that kT noise will be concentrated in the resonances of the system. And if you have dissipation, then it will extend away from those resonances to other frequency beings, and depending on the dissipation you have, it will get more and more expanded to those other frequency beings. So the key in here was to reduce the dissipation so that most of the noise would be concentrated on those resonances. For example, this was the resonance of the strings where the mirror was hanging. That was the first violin mode of those strings. And this was the Brownian motion produced on the mirrors because of those strings vibrating at that moment. So we used to glue magnets on the mirrors to be able to control them with electromagnets. We used to use metal wires. Now we don't glue any magnets to the mirrors. We actually control them from another mass on which we glue magnets. Instead of having metal fibers, we have glass fibers monolithically welded. So with all of that, we think that we can get down here. And here we just use more photons. We use more photons, and therefore you can get less statistical noise in the counting noise. And that's what you get with more power. So this is a curve that we want to get. But if and when we get there, we will be limited at most frequencies by just the quantum noise. That notice that goes up at low frequencies, and that is because you cannot increase forever the number of photons and get better and better. If you have too much power, you begin pushing the mirrors around with that radiation pressure, and that will be random radiation pressure that will be the noise, because it will move the mirrors. So this is like the Heisenberg microscope problem. You cannot increase and decrease the uncertainty in one quantity forever. You have another quantity that's affecting the measurement. Okay, so that's what we want to be. This is the...
Some of the resonances you still have in advanced LIGO because you focus the noises in that frequency.
I'm sorry?
So that the peaks, those resonance peaks, you still have it in LIGO, some of them?
Yes, yes. We will always have resonances. And actually, we want those resonances to be there. We want them to have all the Brownian motion in there.
So the other part out there.
Right. So you want to concentrate it here so it goes away from here. And I'll show you spectrum. So this is what the interferometer actually looks like. It's nothing like a Michelson interferometer. First, the optical technology that we use, the topology, we use well, first of all, as I told you, we use quadruple pendulums instead of single pendulums. This mass is hanging from this mass. This one is the one that has magnets, but then we also have 2 other stages. It looks like 3 other stages, but there's actually 2 horizontal pendulums in here and 3 vertical pendulums. And we do have 4 monolithic, 4 glass fibers forming a monolithic mirror in here. We have that hanging from active seismic isolation, a very complicated system that can be tuned. All of that inside the vacuum chamber, resting on hydraulic actuators to compensate the earth tides. All of that in these big vacuum chambers, this high power laser that can be up to deliver up to 200 watts. And then we have not just a Michelson interferometer with a beam splitter and these mirrors 4 kilometers away, but we also have input mirrors in here, semi-transparent, so these have some calculated transparency to make the light go back and forth in a resonant optical cavity. So this is a Fabry-Perot cavity, this is another Fabry-Perot cavity, so that would make a Fabry-Perot Michelson interferometer. We keep the interferometer so that if these 2 distances are the same, then the interference at the output is destructive, so you have no light coming out. That means that all the light is coming back to the laser. That means that you can use another mirror in here, partially transmissive, to make another cavity between this, considered as a mirror, and this mirror. So that's another Fabry-Perot cavity. That would be a power recycled Fabry-Perot Michelson. And then we have another, this is the difference with advanced LIGO. With respect to initial LIGO, we put another mirror in here that recycles the signal. So this is called the dual recycling because it recycles both power and signal. A dual recycling Fabry-Perot Michelson. And with all of that, and again, this advanced LIGO, different than initial LIGO, not had the lion's share of the contributions of the hardware from the National Science Foundation, but also the Max Planck Institute contributing to the laser, and the UK Science and Technology Facilities Council contributing to the suspensions. So this was an international collaboration even for the hardware. So with all of that, you get noise out of the interferometers, and now you have to find gravitational waves. Now, we look for everything in that. We look for things that don't have a model, that could come, for example, from supernova explosions. So we don't use waveform models for these. We use wavelet templates, or we use wavelets to measure excess power, coherent excess power in 2 interferometers, only considering looking for short transients. We look for periodic signals. Those will be produced by not completely spherical rotating stars. We assume we cannot get farther than our galaxy. In fact, they have to be close, depending on how asymmetric they are. But even with the part in a million asymmetry, we should be able to find some of these nearby. So those would be sinusoidal signals. We all know how to find sinusoids in noise. We do look for these waveforms from binary systems from black holes, neutron stars and black holes. Because of the frequency band that we have, we will only be sensitive to binary systems when the masses are relatively small, for astronomers at least. These would be solar mass objects. Neutron stars have 1.4 solar masses, so those are right in our band, but also small black holes, relatively small. probably less than a few hundred, depending on all the frequency band that we have. And then we also look for noise, astrophysical noise. There could be astrophysical noise coming from, for example, a stochastic signal from the early universe that is expected, or from many, many different coalescences or transients that are all together that they have not resolved. That would look like noise, but it would be correlated noise in the two detectors, so we can find that through correlation. So we have 4 different analysis groups in the collaboration. We have the experimental groups developing the technology. We have the analysis groups looking for all of these signals. The one thing that we can use for the binary systems is the templates. The templates that we know, this growing amplitude and frequency when the stars get closer. However, what we want to know is what happens when they merge. And that turns out to be a very difficult problem. Even for black holes in principle, they don't have radiation, they don't have matter, they don't have hydrodynamics, they only have space-time. And they are the simplest solutions. One black hole was the first exact solution found to Einstein's equations by Schwarzschild. That was a black hole solution. So 2 black holes, how difficult can that be? Well, analytically it's impossible. We needed computers, but even with computers, it was only about 10 years ago that templates for the merger of black holes could be found. And let me show you this movie. Showing you the merger of 2 30 solar mass black holes. I don't know why they chose 30 solar masses. This is showing, these colors in here are showing this curvature of space-time near the black holes on a sheet. So there's a cut meaning in here, although this is happening in all directions. And this is a gravitational wave far from the black holes. So that's the key. You can solve the equations close and far away. And here they're getting closer. This is 10 milliseconds before the merger. These are the horizons. You can see here that they are getting close and close. Here we're getting the amplitude quite a bit larger. And here at 0, they merge. And after merging, they settle down in a single rotating black hole. And this is what the waveform looks like. Look at how simple that is. Turns out that it's so simple, but it's not that simple, but it's simple enough that it can be parametrized phenomenologically, and then we can create templates to look for these even in noise. And that can help a lot to look for black holes. It doesn't help so much for neutron stars, but it helps for black holes. Now I'm telling you the story, you can tell where I'm going with this. How did the detectors progress, the sensitivity? The funding was approved in 2008. In 2010, the initial Ligo era was finished, so we could begin installing the hardware of advanced Ligo. In 2014, early to mid-2014, all the hardware was there, and people began playing with the detectors to see how sensitive they could make it. It takes years to make them work at the sensitivity that you want. It's a very, very complex system with hundreds or thousands, depending on how you count, of feedback control loops. Even though things were going well enough that in 2013, when we were just putting the detectors together, we made a plan. We guessed how the progression in sensitivity was going to be, not only for the Ligo detectors, but also for the Ligo detector in Europe. And then we said, well, we are not going to wait until we get to 100 megaparsecs. We're going to wait until about 2015, when we get something between 40 and 80 megaparsecs, and then we'll take data for a few months. We won't see anything. But then we'll take a break, improve the detectors more, and then take data again. That was the plan. So we made this plan in 2013. We guessed that in 2015 we were going to be in this blue band. in 2017, we were going to be in this green band, and so on. And sometime later, perhaps 2019, it gets more and more difficult to predict in the future, we would get these 200 megaparsecs. Ligo did the same similar exercise. It would take them a little longer because they were funded about a year later than Advanced Ligo. But the idea was that Ligo was going to join us in the second observing run. So here we were going to take data with the 2 LIGO detectors for a few months, and here with Ligo for a few months, and so on. And now this is a part of the story you know. In 2015, we were getting ready to start this first observing run, and just before starting taking data 24/7, this thing appeared in the detectors. It was amazing. We didn't expect it at all. It is exactly what you expected from black holes. It is increasing frequency and amplitude and the nice clean bring down. So it was a gravitational wave. I'll tell you why it took us so long to prove it, but it was a gravitational wave. We had to work on that. So we did, and we published this paper in 2016. Notice that it was the LIGO scientific collaboration and the Ligo collaboration. We worked together in the analysis of the data. And this is how many people signed. Actually, this is only the institutions from the LIGO side, the LSE side that signed, and you might recognize the logo there. That's you. That's actually Professor Shao here. This is a figure 1 of that paper. So this is a signal from the photocell with a minimal filtering, as seen in Hanford. Notice the scaling here. This is 10 to the minus 21. This is a signal in Livingston with a Hanford one, but shifted by 7 milliseconds. So the signal came first to Livingston, we like to remind everybody, and then 7 milliseconds later to Hanford. This is what you can calculate from that simulation I showed you from numerical relativity. The gray signal that you can barely see behind, it's like a band behind the numerical relativity waveform, that is our reconstructed one without using any assumptions. That's reconstructed from wavelengths. So even if we didn't have this numerical relativity waveform, we would have said, oh, look at how simple this is. But now we had the numerical relativity waveform to compare it with, and they were very close. This is a residual that you get when you subtract this from that. This is how you look at it in the time frequency plane, where the color indicates the amplitude of the signal. So you can see that it's getting brighter, it's getting larger, and it's going up. That means high in frequency, and all of this happening in a fraction of a second. So this is a spectrogram that we like to use. Now that was not the only detection we had. I told you that we were going to take data for a few months. We began taking data in September. We ended in January, so we took 4 months of data. We collected about 45 days of live data with the 2 detectors running. We saw this one very, very early on. And then we saw in December 25th in the US, so we call it our Christmas gifts. Officially, we call it the Boxing Day event, December 26th. But it was also a very confident signal of 2 smaller black holes. So now we were sure. It took us months to do this. We weren't ready to confirm it on February 11 when we were talking about this one. But now we were sure. We had detectors that were sensitive enough to see black holes. Binary black holes existed out there in larger numbers than people thought, and we could see them. So this was great time. This is a great time. We also have a signal in here that we call a candidate. So sometimes we say that we saw 2.5 or 2.8 signals. So let me tell you about that. First, let me see if I get sound. I forgot to connect the sound in here. Is there sound? So that I can connect to my laptop. Okay, but
I'm not familiar with the spectral, sorry.
maybe this will work. Let me see. Yes. Let me get it back. I need to connect. Okay, let me try this. Yeah. How many people have heard this in YouTube?
Oh, yeah.
Let me play it for you and then let me see if this is what you heard. I can do this. I can bet that this is what you heard. So there were two signals there. The longer one, almost a second long, was the December one. Smaller black holes coalesce at a higher frequency. That was the 1 second long signal. The other one was a shorter one. That was the first one. That was a fraction of a second. But what I made you heard first that sounded like thump, that was a real thing. If you were paying attention in the spectrograms, I showed you the frequency of these signals, and they were about 100 hertz. They are in the audible range, but that's a low frequency. So the first run I had, that's a natural pitch, the one that you didn't hear in YouTube, although it is there, is the one that's the real one. However, for the announcement and following advice from other people, we said, well, we can add 400 hertz and make it sound nicer. After all, astronomers paint with color, make colors their images, so.
So do you only have a sound from Harvard data? We also have from Livingston data.
Yes, not here, not in
Why not?
It's smaller.
Similar.
The signal, it's similar but smaller. It's smaller amplitude above the noise. The signal to noise ratio in Livingston is lower than in Hanford.
Okay. Why is that? Because scientific knowledge involves
Let me show you. Let me move here. That's a good question. Now that December signal, I cannot show you this nice waveform superposed in Livingston and Hanford and seeing how nice they look together, because that's not how we found it. In fact, that's not how we found the first one either. The way we look for these signals is cross-correlating the template with the data in the detector. So let me show you how that works. Let's assume that this is the data in the detector, and there is a gravitational wave in there. This doesn't look like that of a binary system, it doesn't matter. Let's assume that there is a gravitational waveform, and you know the waveform, you just don't know whether it's there, you don't know the amplitude. So what you do is you multiply you cross-correlate your waveform with the data, and then you construct the signal-to-noise ratio that is a random quantity until it finds a signal in there, and then it has a peak. So it's looking for these peaks produced in the two detectors at the same time, but not exactly at the same time, but within a 10 millisecond window, which is a light travel time window between the two detectors, and produced by the same template. So there has to be several conditions together for this to be a real coincidence. You would say, well, but you can look in one detector and see that it's there. It turns out that when you look at the data from any one of the two detectors, it's not like this. It has lots and lots of non-Gaussian noise, lots and lots of transients, of things that happen in the environment, in the laser, in the detector. So you have lots and lots of peaks for lots and lots of templates. And we use about 200,000 templates. So you cannot see this in one detector. You do need coincidence. Now, even when you find a coincidence, you want to know whether that coincidence happened by chance or not. So how do you do that? You cannot shield your experiment from gravitational waves because gravitational waves go through everything. So you cannot produce gravitational waves. So how do you do that? So what we do is we look for these coincidences over and over again, but shifting the data in one detector with respect to the other. We introduce an extra time shift of 10 seconds, 5 seconds, some random number of seconds, such that if we find a coincidence, we know it's not astrophysical, because there's too large a time window for this to be an astrophysical coincidence. It is just an instrumental coincidence. So that's how we characterize our instrumental background. And that's what we did for this second detection, this December detection. This is the waveform that was hiding in the noise, and you cannot see it. This is the red signal. Notice the amplitudes are smaller in here, 0.6 10 to the minus 21. And the amplitude of the signal, even though it's longer, this here the time scale, but this is about the second. It's longer, but the amplitude is smaller. But this is a signal to noise time series in Hanford and Livingston. And there is a peak, and it is produced by the same template, and it's produced just 1 millisecond apart, so that is a gravitational wave. Now notice that it's not the same amplitude, it's actually quite a bit higher in Hanford than Livingston. That doesn't mean that we have a different amplitude of the signal involved. It just means that we have more noise in one detector than the other. So the signal is the same, but the noise is different, the signal to noise ratio is different. So we do reconstruct the amplitude, but we don't necessarily have the same signal to noise ratio. So that was true. At these frequencies, the Livingston detector was a bit noisier than the Hanford detector for the whole run. So this is what you really look for, a histogram of the number of events that you see versus the amplitude of those events in signal to noise ratio. This is something that we construct from the signal to noise ratio of the two detectors, scaled by chi-square and other quantities. And for the first detection, the September 14, that was a signal to noise, that was a raw, if you want, this detection statistic of about 23. We did a few million of these time shift experiments. We didn't see anything that loud. We only saw about things of about an amplitude of 20. And when we looked at those coincidences, they were the signal in one detector with something else in the other. So when you take out the signal, this fraction of a second from the two detectors and do those time shifts again, this is the histogram we get. You don't see anything louder than 13. So that was a very loud and confidence detection. We could only put a bound of 5 sigma there. It's more than 5 sigma. The second detection, well, the other detection, December 26, it had a lower signal to noise ratio in general. Combined, it was about 13, but still way above this blue background that was left after you eliminated this. Even before you eliminated this, you could have picked it up. So that was also 5 sigma detection. That third candidate, that has a signal to noise ratio of about 11, 10 and a half or so, and it's above this background, and it's a 2 sigma candidate. So it has a 15% chance of being noise. Some people, the optimistic ones, say, oh, it has an 85% chance of being astrophysical. For an experimentalist, 15% chance of being not true is too much. But it is there, of course, so we don't hide it. And it is consistent. If the template that produces the signal is also a template of 2 black holes in between, of masses in between these other 2. So it's probably a black hole coalescence, but we cannot say for sure.
What was this LBT stand for?
LIGO Virgo trigger.
Oh, it's not really GW. That's how you do it.
Well, I'm not sure unless we have better analysis methods, and we might, we don't have a way to take more data and confirm it, right? Because we don't, that it happened in this noise, and this is the background that we have for that noise. So that's the difference with other kinds of signals. Time doesn't help to make this better or worse. Okay, so I need to move really fast. Sorry for taking so long.
Don't worry.
Okay, so detecting is only the first step. Then you want to know what it is. I showed you that these are binary black hole systems, but we want to know what are really the parameters. So what we do is we throw tens of thousands of templates with the parameters close to the ones that found the signal, to the templates that found the signal, and see how well those parameters match the data of both the correlated data in the two detectors. Now there are many parameters that determine the template. There's the masses of the black holes. The larger the masses, the lower the frequencies. There is the final mass and the final spin, and the final mass is not the sum of the initial masses because there is some amount of energy, mass, that is lost in the coalescence. That's the energy that goes away in the gravitational waves. For this detection, it was 3 solar masses going away in energy. 3 solar masses. We calculated it. It's more than all of the visible light in the visible universe in that fraction of a second. Only gravitational waves. And we have the distance. That is what mostly determines the amplitude, but also the orientation of the orbit, because if the orbit is parallel to the plane of the detector, then it has a much larger amplitude than if it is 90 degrees off, and the position in the sky. So all of these parameters determine the frequency, the amplitude, the frequency evolution of the template. So this is what the match of the waveforms looks like with respect to the different parameters. The two these are the two masses, and you can tell that there's one direction, one combination of masses that's much better determined than another combination of masses. This combination is called the Church mass, but that does not give you the independent masses. So when we tell you that the masses were 29 and 36 solar masses, what we do is project these and calculate the 90% confidence limit. So this is 36 plus minus a few, 29 plus minus a few more. So this is what gives you the precision in the masses. The final mass is 62. The final spin is about 0.70, 0.68. That's not such a high spin. The orbit, and that's probably what this is what explains why the signal was so large. It looks like the orbit was almost optimally oriented with respect to the detectors, 400 megaparsecs away. That's quite far away. Notice that that's much, much farther than the distance I was talking about for binary neutron stars. Black holes produce larger signals, so we can see them farther away. The localization in the sky, well, we cannot say much. It's actually not good because with two detectors, you don't have triangulation. You only have the time difference. The time difference gives you a ring in the sky, and the slight amplitude differences and phase differences especially gives you more probabilities to some regions than others. But that's all we could say. Now the masses that we detected are a big deal because black holes we know are born small from 2 neutron stars that each have 1 solar mass, so you get 1 or 2 solar mass black holes. From supernova explosions, you get few solar masses, 10 solar masses at most. And from X-ray studies, we knew of several, not that many, but quite a few black holes, all smaller than 20 solar masses. And of course, none in a binary system, because if they are in a binary system, you don't see the electromagnetic, you don't see X-rays. And here we had two black holes of 29 and 36 solar masses forming 62 solar masses. This was huge. It was not only black holes that had found each other, had time to find each other and form a binary system, but they were big black holes. So astronomers are still trying to understand how these systems form. And there are some theories that are ruled out. For example, the ones that said that there were no binary black holes. We know there are. But this is very good and new information for astronomy. But notice that we are going to be having a catalog of these. This was the second detection, which is quite in line with things that were known before, although this one would be the larger of all the known ones, the 5 black hole. And the candidate is in between. So this is what we will be doing from now on, filling in this catalog. Now the other thing that we do, apart from astronomy, is physics, is testing general relativity. The prediction of general relativity is the one that gives you all these templates and energies, but then you can perturb the templates a bit, and those perturbations are measured as post-Newtonian orders, and then you can try to see how big those post-Newtonian parameters can get as a fractional deviation from GR, so how much you can constrain those. Now there are very, very good limits that we have already on GR from binary pulsars. You do get from this first lowest order parameter a better, I think by now it's better than 1% test of this GR parameter. So this is from the what used to be the double binary pulsar. Now we only see one of those, but it's still we still call it the double binary pulsar. For that parameter, we only have a 20% test. So ours is another test, but not as good as that. But we can use the first detection, this was the first detection, to test the other perturbations in the other parameters. Not as well. I mean, this is order 1, this is order almost 10. We are only testing the order of magnitude. But it's the first time we have tests for these systems here. From the binary pulsars, for the first two parameters, we had measurements, but they were much worse, and then for the others, we only had bounds. And then with the second detection that was longer, we could get even better tests. So the second detection is the one that gives us this, so we still only have about 10%, a bit better than before. But for these other ones, we have quite a bit better parameters and measurements that are a few times better. So this is also going to get better and better with time. Tests of general relativity. Sometimes people ask, will you be able to detect quantum gravity with this? And the answer is no, but we might detect deviations from GR that might lead to quantum gravity.
Excuse me, why there is no 2.5 constraint?
Oh, because in the expansion of the templates, you have B over C to the 1/2, to the 3/2, so those are called 0.5, 1.5, and so on. Don't ask me why. It's a very strange name, but that's the way it was parameterized a long time ago. Now, there are many other results in our one, not any more detections. This is the number of papers we have published. Most of those, we published about 12 papers with the different analysis, the different parameters, estimations, different searches of the first detection, but we have also published many other analyses. So go there and read those. I'm not going to tell you about those, except to tell you that we didn't see anything else interesting. But as I was telling you before, this was the beginning, not the end. We didn't want to detect one gravitational wave. We wanted to have observatories of gravitational waves. So we took this first observing run, data with this observing run in 2015-16. We began in November 30th with this second observing run. We worked on the detectors in here, and I can show you. We got a bit better in Livingston. We got a bit worse in Hanford, trying to use a higher power laser, and that turned out to be more complicated than we thought. So we are now between 60 and 100 megaparsecs, but we are going to be taking data until August, so we expect to see something. We'll announce it as soon as we have things to announce. Virgo, the big news will be here that Virgo will join, we hope in a month or so, the run with lower sensitivity, but then if we have a strong detection like that first one, then we have a better localization, just because Virgo is there, even if it has just a decent look. And then we again shut down for about a year. We plan to make several improvements in here. We hope to get to around 150 megaparsecs. If we really get to more than 100, significantly more than 100 megaparsecs for binary neutron star range, in a year of data, or about a year of data, we should see a binary neutron star coalescence. And if we are very, very lucky, we might see an electromagnetic counterpart to that. So that is something that will be coming. And of course, we keep working on this until getting to the goal of 200 megaparsecs. Now these are the spectra that we have in O2 it's 70 megaparsecs binary neutron star range for Hanford, about 84 for Livingston, but it goes up and down, of course. For black holes, it's much larger, about the same as before, but it's about a gigaparsec. This is what I showed you before. I wanted to show you what we are here. For the first observing run, the detection, the sensitivity that we have was better than we had guessed. We were at the bottom, except here, we were at the bottom of that blue band that we had guessed for that first observing run. And we were happy to be there. After all, we got the detection, 2 detections. This O2 run is not as good. It's just a little bit better because of higher power, but this is what Livingston needs. It's a bit better, 100 megaparsecs, we're just getting there. But for O3, we plan to use several other techniques like squeezing the vacuum to get better sensitivity, more power, less losses, less scattered light. So we think that we can get there. Of course, it's difficult to promise, but if we get there for O3, then binary neutron star coalescences within a year of data are quite possible. But it's going to take a little while. Now, you might also know that we do share our triggers with as low a latency as we can with our astronomer friends. So we have lots of astronomy groups that with whom we have signed agreements. So we send them alerts as soon as we can above a very low threshold. That SNR is like 6. Remember that 2 sigma detection was at 9. So 6 is very low. Most of these alerts will not be detections at all. But they only happen, we only send them out about once a month. That is the definition that we have, and the false alarm rate of once a month. So they are willing to look in the sky for those things. So we did do that for the first observing run. There wasn't any definite counterpart. There were some interesting things, but nothing that I would call definite. And we do that with all kinds of telescopes, visible infrared, radio, X-rays, gamma rays, and also with particle detectors, like neutrino detectors. Now, for doing this kind of multi-messenger gravitational waves, localization in the sky, not just in time, is important. And I showed you that we didn't do that very well. Now, before going further, let me show you the latest news. We do publish in Ligo.org about once a month an update on how much data we have collected. We have now collected about 67 days. For O1, we had collected about 45 days. So we should be getting detections, and as soon as we know about those, as soon as we confirm those, we'll let you know. And we have, as of April 23rd, we had shared 6 triggers. But again, those are very, very low threshold triggers, so you should not interpret that in all X6 detections. There might be no detections, there might be few. Now the triangulation, as I mentioned, is very poor, even for that strong signal, even poorer for that lower amplitude signal in December, so we need more. And we need more detectors. We are getting Virgo in the second observing run, so that at least we have triangulation. It's important to have detectors with same sensitivity, so it will still take some time until Virgo gets there. But Kagura in Japan is going to get there. We expect them to be at the decent sensitivity about 2019 or so. And in India, there's a Ligo detector to be installed. All of these things are going to take some time. But the next decade, we have a network of gravitational wave detectors, not just LIGO detectors. That helps the sensitivity, it helps the localization. It's going to be a decade of very exciting detections. And that's not everything, that's not all, because we already have ideas on how to improve these. Now, for improving the ground-based detectors, LIGO, Virgo, Kagra, all of these, one of the roadblocks is that Brownian motion I was talking about. The group here in this university is working on fighting that kind of noise, on getting low dissipation materials in our mirrors so that that Brownian motion does not constrain. So if and when that problem is overcome, then the sensitivity can get a lot better. We can go, this is the sensitivity expected from advanced LIGO. This is installing several improvements that we could make, including lower dissipation materials on 4 kilometers facilities, but then we dream with larger facilities that would improve the sensitivity. There's a conceptual design in Europe already called Einstein telescopes with 10 kilometers triangular design, underground and cryogenic. So we can get 10, 20 times better sensitivity. And remember that more sensitivity lets you see a volume that's the cube of that improvement in sensitivity. So that's a very big deal. Of course, those are expensive and they will take 20, 30 years to build. That's what initial and advanced LIGO too. But they are coming. And our band is not the only frequency band for gravitational waves. There are gravitational waves of lower frequencies. We don't think there are gravitational waves of higher frequencies, at least of astrophysical origin. But there are the massive black holes that produce gravitational waves of periods of minutes to hours, and those will be seen by a space detector that's called LISA. It's funded by the European Space Agency. It will fly in 2032 or 34, so it's also going to take time, but it's coming. Lower frequencies from supermassive black holes and from the early universe can be measured with the radio signals that we see from pulsars, because we can see those radio signals on Earth and use those beams as the beams of an interferometer. So now you have an interferometer of galactic scale. That is how long the wavelength you can measure. And this should be seeing signals already. I could bet that they are going to see signals either from a stochastic stationary background or from supermassive black holes within 5 years or so. And then there's the early universe, and that is very difficult to see because it's either very low amplitude at these frequencies or very low frequency for these. So what the best bet for those is to measure the imprint of the gravitational waves on the electromagnetic waves of the cosmic microwave background. They determine the polarization of that CMB, of that cosmic microwave background. So if you can distinguish the polarization of the CMB produced by dust from the one produced by gravitational waves, you will be learning about gravitational waves of the early universe. So gravitational waves are coming in all of these wavelengths to us. a very exciting time. Sorry for taking long, but I'll take many questions.
So now, questions? Yes, please.
So very nice talk. So as you're talking about, you're expecting a neutron star binary detection before long time ago, but now you have detected mostly black hole mergers. So I was wondering, what's the future direction? Do you want to focus? I saw some slides. You saw a setup of the neutron star optimized setup. So what's the future direction? Do you want to focus on black hole mergers, or you're still going to try the neutron star optimized way?
Well, the answer is yes. Yes to everything. We'll try to get better at all frequencies. Let me show you what the plot you were referring to. This one. So what he was talking about is that this is the advanced Ligo design. So this is how well we can, how good we can get with the technology we have, depending on the transmissivity of the signal recycling mirror that we use. We could make the sensitivity worse at some frequencies and better at others. And this is one that's BNS optimized because it gives you more signal to noise ratio of these frequencies near the merger frequency of the binary neutron stars is 0.5 kilohertz or 5 kilohertz. So where to focus? Well, the focus for now is to get here, to get to the black curve. Once we get there, we will learn a lot more about both, we hope, neutron stars and black holes. And then we have a strategy on how to optimize technology in the future. But the technology we have now is it's mostly for this region. In this region, let me see if you see, this region is the most difficult one. So we are focusing on that one because that's what we are doing the worst. And these are all technical, what we call technical noises. These are electronic noise from our angular systems that have to work too hard because they are coupling with other things. So we are working on that, if you want to say. We are focusing on the low frequency region. But to get it here, once we get here, then we'll see what to do. We don't have any strategy yet.
Well, this low frequency is more important for more massive black hole, right? So
it is, but it's also very difficult to prove. So.
Right.
Yes.
Okay. I'm curious. Combining LIGO and Virgo or Vigo, how precise you can determine the location of gravitational wave source? And in the future, how precise you can achieve to collaborate with astronomers' data?
Well, our calculations say that with all three detectors working at the best sensitivity, this kind of sensitivity, we get to a fraction of a square degree or a square degree for about half the detections. So that's still too large for astronomers, at least for most astronomers. And it's going to take a while to get there. On the other hand, the release, the sky map that we had for the first detection that was very strong, it had 600 square degrees. We refined it later to 250, but that was months later. If Virgo had been working at the 20 megaparsecs that we hope that we have in a month or two, instead of 600 square degrees, we would have had, I think it's 50 or 100. So it helps a lot.
Yeah. Oh, I'm just wondering, have you studied about the theoretical limitation of this kind of technology? I mean, it seems like you're finding off analogically. You're reaching to the close to the theoretical limit about sensitivity. Research by the sensitivity principle or fundamental law of physics. So
yes.
If you don't change the design, someday supposedly advancing technology, eventually we'll reach a limit in which we can look at like an optical telescope and look at different rain or that we actually pick up. So have you studied about what we need to reach, and then are there any new technology or new design that use to beyond the interferometer use?
I think that if there is a fundamental limit in sensitivity, we don't yet have a good sense of that. And let me show you an example. We thought we did. There was something that we used to call the standard quantum limit, which was this Heisenberg that I was saying, if you use too many photons, then you begin radiation pressure, so it's a trade-off. There's a minimum uncertainty you can get. We can get around that. We can get around that now because we can use this squeeze light in which we squeeze the uncertainty in one direction by increasing it in the other. We squeeze the uncertainty in phase, which is what we measure at these frequencies. We squeeze the uncertainty in amplitude at these frequencies, and we know how to do that now. So we got around that fundamental limit. So there isn't any fundamental limit that we know of. There are things here we are limited by gravitational gradients, which is the Earth moving around and attracting our mirrors, not through the ground, not through the suspensions, but just Newtonian attraction. But we think that we know how to subtract that. We are limited by Brownian motion, but that looks like material science. We are limited by quantum noise, but we can squeeze.
So there's no need at the moment to go beyond the interferometer?
Well, there is if you want lower frequencies. If you want lower frequencies, then yes, you need some. There are some alternative designs for interferometers that are atom interferometers. They have been proposed. There haven't been any prototypes that have proved the noise. The consensus, at least among our field, is that they would need frequency stabilization of the light that they use, which is similar to this, and with that kind of frequency stabilization, then the two would be competitive. But then that needs to be proven. But other than interferometers, even the space ones are interferometers conceptually. That seems to be the best bet.
Okay, question over there.
Yeah. Thanks for a great talk again. I have two questions. First one, do you also use redshift to determine how far the binary is? This is my first one. And the second one is, I learned Ligo and Virgo community are excited about an effect called echo. Can you say something about that? Thank you.
About the first one is, sadly, no. We cannot determine the redshift from our observations, so our distance estimate is uncertain by the redshift. We have to estimate. We have to use some cosmological model to tell you that it is 400 megaparsecs. However, for 400 megaparsecs distance, the redshift is only 0.1, and we have larger uncertainties than 10%. So redshift is a small effect at this point.
Okay.
For the second one about these echoes, it's still under discussion. Our analysis seems to say that there is no such thing, that we don't, for people who haven't heard about this, there are some publications that show that, seem to show that there was a gravitational wave detected, but then there were others before. I think I remember what before. So they're called echoes, and there are some theories on how that can be produced. We have seen similar things that are artifacts of doing the analysis, mixing up the many lines that we have in our spectrum. It turns out that analysis seems to be simple when you do simulations, but when you want to use it on data that has this many lines in there, it's a lot more complicated. And when trying to subtract these lines, you get sometimes into artifacts that look like echoes. So we haven't found, in our analysis, we have not found those same results.
Thank you.
People begin to talk about using gravitational wave to detect the wave transition in the early universe. Will the new technology have such sensitivity to that?
Sadly, I don't think so. At least this kind of sensitivity. Because at these sensitivities,
the new technology, I mean the new like triangle
Einstein Tensor.
the Einstein,
Einstein telescope.
even the Einstein telescope. Well, let me show you those scales, just to give you an order of magnitude. But this is 10 to the minus 25. The predicted amplitude of the early inflationary background is 6 orders of magnitude below this. Of course, there might be phase transitions that produce the background that's larger than that. It is constrained by the nucleosynthesis. The Big Bang nucleosynthesis puts limit on how big the inflationary background is, because if not, it doesn't work and the elements don't form. So there's a limit on a broadband limit on that.
I have a question about the collaboration with the electromagnetic telescope. So if we want to do the follow-up observation of the gravitational wave source, so we need a quick alert of the detection. So but I found that you need to analyze the data to make sure that the detection of gravitational waves. So how quickly do you?
Well, we have shared, even in the first observation and now these alerts that we talked about, most of those we have shared within a day, some within hours. We are trying to get, our goal is to be minutes.
Okay.
We do have an analysis that produces the triggers in a computer and sends text messages to different phones within a minute or so. We still have a human step looking at that, and actually about half the time for alerts we have found that there was some false alerts and things that are instrumental, obvious instrumental artifacts. So we are not yet in the automated phase, but our goal is to have automation for minutes, and we think that we will have that ready by the third observing run. In the third observing run, we plan to have public alerts, not just alerts to people with agreements, but public alerts.
For GRB after growth stage, we are talking about seconds.
Yeah.
Seconds.
That will be
so
more
the
difficult.
announcement
Yes.
within seconds.
But on the other hand, for GRBs, we can do the analysis backwards,
Yeah.
right?
Yeah, because people are monitoring GRB all the time. All the time. Yes.
Okay. If one uses a slow line in the interferometer, then it's a few kilometer long arm that becomes a few centimeters. Have you considered such possibility? Do not slow line, just light propagate very slowly.
Yes.
Then reduce to the sound speed by 5 or 6 order magnitude.
Yes, the problem is having cavities with these technologies, right? All of this sensitivity relies on optical cavities, resonant optical cavities controlled, and I think
What you need to do is to make professor use that larger than you have a cavity.
Because your cavity becomes a few centimeter long. We are using slow light, probably very slow. So I'm just wondering whether you consider such possibility in Ligo project or not.
not directly, we are waiting until seeing technologies. Ligo technology is more like applying technology from other fields into this rather than inventing new technology. So there's nobody developing slow light for this. People are waiting to see that experiments with slow light and other things are easier and again are proven to be standard optical technology. Let me tell you that for some of these sensitivities, for example, assume a longer wavelength, and already that is difficult because you have to think about new mirrors and new coatings that have the specs that you want for those wavelengths. So that's what I mean. It's practical difficulties.
How well can you control the speed of light?
Yeah.
How well?
How well? Again, as I said, it's reduced to 5 or 6 order magnitude.
About everything has
How well accuracy?
Accuracy. Over a period of time.
Because this is interferometer. As long as you propagate in the same speed in 2 arms, then you can do the interferometry.
For how long the period instead of staying such slow?
Well, okay, I understand. There's a lot of technical problem.
All depends.
We need to have another workshop. Slow light is kind of is a general physics. It can work in any system, solid system, and order system. It can work. Okay, I think also squeeze light. You can make squeeze light probably also very slow. So that's some possibility. I don't know whether you have explored.
Yeah, no, I'm saying that it's like atom interferometry. I mean, conceptually, it's all possible. The question is to see it working on small lab prototypes. That's how this field started. It was all small prototypes that became 1.5 meters, 40 meters, then 4 kilometers.
Yeah. So more questions? Oh yes, too many.
I'm curious about one thing is, so far the 2 successful detection from LIGO has one thing in common is that are all single events. So what if one day the LIGO detect 2 or more gravitational waves pass through and they are come from different directions, different places? Can we detect it or not?
Yes, actually, we have one of the papers that we published soon after the detection shows that if you extrapolate for when we reach this advanced LIGO sensitivity, although you might have to be a bit better, you will begin to see a stochastic background, a noisy background produced by low amplitude signals. These are coalescences of black holes that are far away, so they're small enough that you cannot detect them, resolve them individually, but all together they form a noise that you do detect in the true detectors because it's correlated noise. So we will find when we search for a stochastic background, I told you before that one of the things that we search for is a stochastic background that could be produced by early universe stochastic background or by unresolved signals. We think that we will see that unresolved background, that background of unresolved signals at the high frequencies of advanced LIGO sensitivity when we get there. So that might end up being a limitation, well, not a limitation, but some people would call it noise, some people would call it signal, but we would be having a gravitational wave background at these frequencies. I look forward to seeing that.
Yeah. So it's so sure the gravitation wave is detected but about the explanation, say this comes from the binary black hole. Have anybody considered from the 3-body or 4-body system?
The experiment and the detected waveform that I showed you that we reconstruct and the one predicted by numerical relativity of a binary system is so close that you can discard a perturbation produced by a third body. You cannot measure spins very well, so the spins of the systems have a much stronger effect. But it is something that people are wondering now. How long will it be until, if binary black holes are so common, then at some point there might be there might be 3 black holes. But they would have to be close together. The problem also when you have when you have 3 bodies, is that in general 2 are much closer than the third one. So the third one is just a perturbation on the binary system.
So you have
Okay. So regarding the question about positional accuracy, I think you mentioned like later you narrow down the error circle to 50 square degrees. I think that
250.
okay, 250, but still like 600 square degrees and 250 square degrees makes a big difference for astronomers. So I wonder if you had some faster computer, can you make this better positional accuracy available in a realistic time scale for follow-up observation? Well, what's the limitation here?
It is, well, maybe this plot. So the better accuracy, so these are histograms of the different ways of localizing, different methods of localizing the signal, but also using different parameters. So first, if you get good parameters for the masses and the orbit, then you can get better, narrower pieces in here. However, the much more efficient way is to get another detector in there.
Right.
So once you get a third detector, then the reduction in those uncertainties in those circuits will not be as dramatic.
So is it not possible to do this process in I don't know, a day or two?
These simulations, I think, took 2 months, 2.5 months.
With, I guess, like a pretty good computer.
Well, more computers always help.
All right. So
you said you can only run 6 triggers.
We have shared 6 triggers, but
These are the more likely candidate.
Random noise.
yeah. Let me
Sorry.
let me give
Random
you
noise, right?
let me give you an idea. These for this candidate, we could set a false alarm rate of 1 per bound of 1 per 200,000 years. So this happens by chance only once every 200,000 years, or more or less than that. This one would happen by chance once every 3 years. The threshold that we use for sending something to astronomers is 1 every month. So it's down there in amplitude.
So can you share personally how many of these you think eventually we need?
No, because we haven't quite finished analysis.
And how long will it take to finish that? When we will start to hear about
it took us 4 months for this one, 4 months for this one. So it's
that.
about 4 months since we started. So
are all 6 black hole mergers? Or is there any
of those?
or single events?
Well, that is not public information, but no, they are not all public.
Oh, they're not interesting.
They are not. No, we do several. In fact, we do share with astronomers triggers produced by searches for binary systems or searches for short transients, generic searches by short transients. This was found by the generic search for transients. These two were not because they were low amplitude. But these generic searches for low transients do have a background. We have published the paper that we published showing the results of that search, and this one in here, and a background, and the rest of the observations all consistent with the background. So, by now, the histogram was similar to this, so we saw about 10 or 15 bursts of noise that seem to be produced by astrophysical transients, but were consistent with our background.
All right, so one last urgent, very short question. Is there anyone? Okay.
You intimidated everybody.
All right, if you are happy, then let's thank Professor Gonzalez again.